Today we study C24 of Escape from Scientific Absurdity. So you can download the PDF file for this lecture if following this way. So please type in kpop.org, kpope.org, and scroll down to find the table of contents. So there's an escape from scientific absurdity. We are working on the series C, and C24 is over there. If you click this button, you will find the PDF file for this lecture. And if you click after this lecture, I will upload the video to our K-pop YouTube homepage. And if you click this, you can watch the lecture in Korean, and the button next to E represents the lecture given in English. You can click this in the middle to return to our K-pop digital library. Connection in my office is very, very slow, so I don't find. And then if you click this, you can freely subscribe to the K-pop YouTube channel. Okay, let's begin with C24. Establishment of Lagrangian and Hamiltonian mechanics. So we have found that the three Kepler's law of planetary motion were completely explained by the introduction of Newton's second law of motion, with the external force on a planet is actually the universal gravitational force with applied by the sun. Okay? The concept of energy was not known to Newton. Although many people misunderstand that Newton knew about the energy, and the introduction of a conservative force corresponding introduction of the potential energy for a conservative force greatly simplifies our problem solving, because it reduces a problem into a scalar instead of a vector field. Force is a vector field, but from a potential energy, we can take the minus gradient to derive the force field that is a vector field. But computation in the scalar space is mathematically much easier than dealing with a vector. So we investigate the brief history of the development of the modern concept of energy. It took about 100 years after the discovery of Newton's laws. What are the conservative physical quantities discovered by Newton? Let's see. Newton's third law is very important to find a conservative quantity. The net force applied to the closed system consistent of particle 1 and 2 of mass m1 and m2 is the sum of the force applied to particle 2. 1 and 2 communicate with each other through the interaction. So 1 applies force to 2 and 2 applies the force to 1, and their forces are equal in magnitude, but directions are opposite to each other. Therefore, the algebraic sum of the two forces is identical to 0. So they are mutually additive inverse. Okay, from which we apply the Newton's second law, the force applied particle 2, not this, particle 1 is the mass times acceleration of the particle 1. The force applied to particle 2 by particle 1 is the m2 multiplied by the acceleration of the particle 2. We know this is nothing but the time derivative of linear momentum that is a product of mass and velocity. And for the particle 2. So this one is identified with the particle 1's linear momentum. The sum of the linear momentum is called the total linear momentum of the system of particles. In the case of two-body system, we just add the two momenta of the particles. Now, the time derivative of total linear momentum of this closed two-body system is 0 because the net force applied to the system cancels because the internal forces cancel exactly. So this is the first important one Newton has discovered, that is the conservation of a total linear momentum. The linear momentum conservation is the generalization of this two-body case, and whatever particles may exist in a system, closed system, the total linear momentum must be conserved always. In addition, we have another version of Newton's second law, that is the rotational version of Newton's second law, and we can generalize idea of the linear momentum to the orbital angular momentum to consider the rotation of a system. The orbital angular momentum is the cross product of position vector and linear momentum of each particle, and this for each particle, the time derivative of linear momentum is torque. Torque is defined by the position vector cross product with the net applied force. Here, we find that this first term cancels because the linear momentum is parallel to the velocity. So we have P dot equals F, force. So this is the linear version of the Newton's second law, and an orbital angular momentum's time derivative is torque. That is the rotational version of the Newton's second law. This one applied to a system of particles, then we can reach the point that total linear momentum is conserved. This rotational version of the Newton's second law will result in the conservation of a total orbital angular momentum as long as the force is central. That is, central means the force between two objects is parallel to the direction connecting the two particles. However, even if many of you might misunderstand that the Newton knew about very well about the energy, however, in fact, Newton and Descartes, they were not able to find a solution for the elastic scattering problem, for example, the collision of billiard balls, because they, even though the Newton knew about the linear momentum conservation, the energy conservation should also be used to determine the unique solution for the collision problem. Okay, Who is the person who extended Newton's laws applicable to a rigid body? This is also many of us have misunderstand that Newton found everything, including the rigid body motion. Newton's law of universal gravitation was applied to the two-body system, but the actual application to spinning top or a complicated mechanical problem involving rigid body motion was achieved about 50 years after the original formulation of Newton's laws of motion. It was found by Leonhard Euler. So many of you might understand that Euler is a pure mathematician. He is the physicist and he established classical mechanics very much. So the F net equals linear momentum's total linear momentum's time derivative is the net force applied to a rigid body. It was Euler's first law. And Euler is the one, he generalized this idea to a rigid body system. And this, many of you, and we have this considered the fact that some of many particle systems linear momenta can be expressed as a sigma notation or the integral form. So this total linear momentum can be generalized to a rigid body using this formulation constructed by Euler. Euler has another law, that's Euler's second law, that is the rotational version of the Newton's second law applied to a rigid body system. So we have to thank to Euler for the construction of realistic mechanics theory applicable to rigid body motion. And we are all familiar now with the rotational inertia or momentum inertia. That is very important point, just like the mass in the linear momentum. But angular momentum involved instead of the mass itself, but mass weighted by the lever arm square. That is the momentum inertia. And the momentum inertia concept was first introduced by Huygens, who constructed the pendulum clock. Generalized idea first obtained by Galileo Galilei. And then Euler achieved a lot. He demonstrated his second law, and the terminology of momentum inertia was first introduced by Euler. Euler is a very, very important person in science and mathematics. He popularized the pi, introduced the convention of writing function as f of x. He introduced into this I for square root of -1. We remembered Euler's formula e to the I theta, there's cosine theta plus I sine theta. And he also introduced the summation notation because it is very convenient to describe the motion of a rigid body by dividing into many, many pieces, small pieces. He also introduced the notation for delta for changing a function, differential. And by the way, the integral notation was introduced by Leibniz. And in solving physics problem or mathematics problem, many of us used capital letter for the point of a triangle and A and opposite opposite side to the lowercase. This convention was also introduced by Euler. So he's a very smart person. Next, we are approaching the concept of energy. The first primitive concept of energy is vis viva. It is identical to the kinetic energy, what we know, but kinetic energy is not mx dot square. It factor of 1/2 is missing. Leibniz and Bernoulli introduced vis viva. And finally, it was experimentally tested, and Émile du Châtelet, who translated Newton's Principia into French, was able to publish this result that kinetic energy is proportional to mass times velocity squared. And why don't you read it through for more details about the development of concept of energy. And we'd like to concentrate on the work by Euler and Lagrange. Euler introduced the calculus of variation, and Lagrange constructed delta algorithm leading to Euler-Lagrange equation. We shall find that the Euler-Lagrange equation is equivalent to the Newton's second law. And then Hamilton applied the variational principle. This variational principle we will study in detail later, the later part of these lectures. Just the most important point, the difference between the Newtonian mechanics and Euler-Lagrangian mechanics, it is simply called the Lagrangian mechanics, is that they use energy instead of a vector, the force field. So they use the energy. We know kinetic energy and potential energy. They were very smart to find that Lagrangian hold the difference between the kinetic energy and the potential energy, and from which they have shown that the F equals ma. For simplicity, in one-dimensional case, F equals ma is equivalent to this Euler-Lagrange equation as far as the L Lagrangian is the kinetic energy subtracted by potential energy. And this coordinate x is generalized to q because sometimes the coordinate x is required, and sometimes for rotation, some angle that is dimensionless is required. In any case, Lagrangian mechanics works fine. And there were two kinds of versions for Newton's second law. That is force. That is the force is time derivative of linear momentum, and torque is a time derivative of orbital angular momentum. So they are all unified into a single piece from this Lagrangian. You can derive the linear version and the rotational version. So it is much easier to derive the equation of motion of Newton. Okay. What about the least action principle? Hamilton, in addition to the Euler-Lagrange equation, Euler-Lagrangian mechanics, on top of that, he introduced a very simple idea. He defined the action that is the time integral of Lagrangian, and Lagrangian was kinetic energy subtracted by the potential energy. Hamilton showed that the action is minimized along the path that is physically allowed. And that is called least action principle. And least action principle derives the Euler-Lagrange equation. And because of the proof by the Euler and Lagrange of the equivalence of the Euler-Lagrange equation and Newton's second law, so Newton's laws of motion can derive from very simple idea, least action principle. So the current theory of physics is based on a very simple deductive method, so based on the least action principle. That is very, very useful because it does not fail in even in the non-relativistic case as well as relativistic case and electromagnetism. And furthermore, it's this mechanism works for relativistic case and electromagnetic case too. All right. We finally show the Euler-Lagrange equation is equivalent to this F equals ma. We shall find more detail how to derive the equivalence, how to show the equivalence. And today, you please uh, make yourself familiar with these expressions and names. And this is called action, and this is called the Lagrangian. What is Lagrangian? There's kinetic energy subtracted by potential, and just memorize, and we will find a relationship among them. This Hamiltonian mechanics derives after the introduction of the least action principle. Hamiltonian is to us, it is nothing but the total kinetic energy of a mechanical system. Hamiltonian is closely related to Lagrangian, and we have P momentum and Q that is a coordinate. I told you the coordinate could be a linear coordinate with the dimensions of length, and it could be an angle variable. But for each coordinate, there should be a corresponding conjugate momentum. For example, x, then we have m dot x dot, that is called the linear momentum. For an angle variable, we have moment of inertia and angular velocity, that is orbital angular momentum. For each case, for any case, we have simply Q to P, their correlation among between the coordinate, any coordinate, whether it is a dimension full of or dimensionless, just like angle. The relation between the coordinate and the conjugate momentum was found, and that conjugate momentum can always be found by taking the partial derivative with the velocity of that coordinate. So we have to remember Q is a coordinate and P is a corresponding conjugate momentum conjugate to the coordinate Q. And this coordinate can be either the position vector's coordinate, Cartesian coordinate, or angle. Eventually, Hamilton found that this equation, this F equals ma, and Euler-Lagrange equation can be bisected into two parts. So, and this they are coupled first order differential equation. So this is a second order F equals ma, and Euler-Lagrange equation is a second order differential equation. And Hamilton found that they are decoupled into two pieces, and when you couple them, you can reconstruct the whole equation of motion originally developed by Newton or Euler and Lagrange. Okay, what is the earliest publication of containing the correct expression for the kinetic energy? 1/2 mv squared. You can find the book of Coriolis. This is a mechanics book. All right. You will find the potential concept of potential energy was developed already by Euler and Lagrange, but it took a very long time to appear in textbooks. So they appeared very, very late. And now we learn everything all together. And many of us misunderstand, and the even textbooks do not say they were not all of them were found by Newton, but it took more than 100 years to achieve the knowledge what we have acquired until now. That's it for today. Thank you.